The presentation is about quantifying the effects of preservation treatments on the performance of pavements. It is based in its entirety on NCHRP Project 1433. And before I do get started, I want to acknowledge three people. Two of them are here in the room. Gary Hicks was part of the research team. Dave Lohr was the chair for the project panel, and the third person is not here, but James Bryce, a young engineer who has an incredible arsenal of analytical tools that was extremely useful on this project. Okay, I'm going to spend a couple of minutes providing background information, but then the bulk of the presentation will be on the findings of NCHRP 1433, including the recommended performance measures, as well as the validations of those measures. And then I'll again spend a minute or two just summarizing the major conclusions and recommendations from the project. So moving on with the project background, pavement preservation, or at least the definition that we used in the project, is a set of activities intended to maintain or improve the functional condition of pavements at a relatively low cost, and generally when pavements are still in good condition. Now, the figure that you're looking at here on the screen is trying to illustrate the effects of pavement preservation on performance. And there are two effects, really. There's not one of them. The first performance, and I'm sorry. The first one is what you're looking at here. There is an initial condition change, sometimes referred to an initial condition jump. So that's what happens immediately after the preservation treatment is applied. Then the second effect is really what happens over the long term. How does the treatment affect the long-term performance of the pavement? And that's really what I'm going to focus on. And that's critical, because if you can quantify those effects, then just about anything you want to do in terms of decision making, whether it's timing, whether it's service life extensions, whatever, you have the basis for doing that. In terms of the objectives of the project, the first and foremost objective was to identify or to develop performance measures that consider the contributions of preservation on pavement performance, service life, and life cycle costs. This is straight from the solicitation. And assuming that that objective was successful, then the second one was to develop a guide for the implementation of those performance measures. There were two phases to the project. The first one focused on the identification and the evaluation of performance measures. This phase began with a literature review. And from that literature review, we found an incredible number of performance measures available there. We grouped them into four general categories. One of them, individual distress or conditions, that included IRI, rotting, faulting, cracking, all of these things. A second group also had quite a few of them, the composite pavement measures, and I think you've heard a few of them referred to here. Pavement condition index, various versions of it, pavement quality index, pavement condition rating, etc. There were a number of cost-based measures. An example is the equivalent uniform annual cost, which is used here in the state of Washington. And then there was a fourth category, a catch-all category. Other measures included such things as noise, RSI, that's a remaining service interval, asset sustainability ratio, etc. Concurrent with the literature review, we did conduct a survey of U.S. state and Canadian province highway agencies to get information not readily available in the literature. We did have a number of follow-up interviews with many of those agencies, but the questions were all either related to performance measures or to preservation treatments. And a lot of important information came up as you're looking at here on the screen. This happens to be common. What are the more common preservation treatments? You'll notice that in the case of asphalt treatments, by far, thin overlays, 88% of the 42 agencies that responded use it, followed by chip seals, 79%, and microservicing. That's important because those are the treatments that we focused on in terms of validating the performance measures. Same thing, but now on the Portland cement concrete side of things, you'll notice that by far diamond grinding, partial depth patching, and joint sealing are the more common treatments. Now going back to the literature review for a second, we found a lot of different definitions for performance measures, which again was the focus of the study. And while there were a lot of definitions, they had sort of a common theme. So the definition that we adopted in the project is that they're basically metrics that quantify the degree of achievement towards the specific goals, objectives of an agency. And that in turn has a number of implications. Number one, those metrics must be able to capture the current condition of the payments. And number two, those metrics need to be able to take into account actions and their impact on the condition of those payment assets or payments in the future. Now, to make a long story short, the performance measures that were recommended in the study are summarized here at the bottom: IRI, cracking, faulting, and rotting. There were a number of reasons why. For one, for example, they are the drivers for maintenance decisions. Another important reason is that the data are available to work with those performance measures. Yet another example, MAP 21 and the FAST Acts require, in essence, that these data, these measures be used. So this does not mean that you have to use them. Ultimately, the bottom line is that the performance measures that an agency adopts needs to be tailored to the specific objectives, the strategic objectives of the agency. Second phase of the project focused on the validation of those performance measures. And as part of this effort, we collected actual real data from 8 different state DOTs, as well as from the LTPP program. Those data at the very top included payment condition versus time data, both prior to the treatment and after application of the treatment. It also included information about the various factors that affect performance: structure, subgrade soil, traffic, and climate. Now, we covered with those data, 6 different AC preservation treatments: thin overlays, chip seals, slurry seals, microsurfacing, and I'm not sure I remember the other 2. In the case of PCC, they were diamond grinding and dowel bar retrofit. Now again, going back to the start of the presentation, the effects that we were looking at were this initial condition jump and the long-term effect. So if we start with the first one, for the initial condition jump, basically we looked at the data. What was the condition of the payment prior to the treatment, which is shown here, and what was that condition after treatment? So if this is cracking 20%, afterwards 3%. And that's for one payment segment. For all payment segments within a combination of performance measure and treatment, we basically plotted those data. We developed a regression, which is what you're looking at here, to look at the change in the stress as a function of the initial condition of the payment. And actually, let me go to the next slide, which shows exactly the same thing, but looking at real data. This is the impact on thin asphalt concrete overlay on the IRI value. On the x-axis, there are 3 plots here. The top one happens to be LTPP data. The one here happens to be Virginia DOT data between 2007 and 2014. And the one at the bottom, Ohio DOT data. They're all the same thing, looking at the initial condition jump. On the x-axis, you have the IRI before the treatment, before the thin overlay. And then on the y-axis, you have the decrease in IRI as a result of that thin overlay. A number of things that I'll point out from this slide. Number one, you'll notice there's a point circled here in red, which is an outlier. And there's different ways you can deal with outliers without necessarily eliminating that data point. But if you don't take into account for that outlier, this dashed line is what you get. You get a horizontal line, which basically says it doesn't matter what the condition of the payment is. before the overlay, the effect will be the same, and that's not really true. If you take that point away, you get this green line, and that green line is almost identical to what we got from the Virginia DOT to what we got from the LTPP data, and that's very important. Second important point to look at here is that the worse the condition in terms of IRI before the thin overlay, the greater the decrease in IRI. In other words, the greater the impact of that thin overlay on the condition of the pavement. So, for example, in all of these, if you start at 250, you do a thin overlay, the reduction is going to be around 140, 110, 100. It'll go back to around 100 plus. And you'll also notice that if you take it around 100, the change is little. You already have a fairly smooth pavement. 3 data sets are giving us very similar results. Moving on then, so we can do a very good job, and the data are there to establish that initial jump. So now the second part is the long-term effects of preservation treatments. And here there's different ways that you can do it. The way we did it is we basically, for a given pavement segment, we took at the pavement condition history over time. And we developed regression. We found the slope, or better yet, we found the growth rate for that particular distress. So here's one segment, here's another segment, here's another segment. All of those segments within a given grouping of performance measure and preservation treatment. And if you plot all those slopes or those growth rates, y-axis, versus what the condition prior to the treatment was, you can come up with a regression that will give you the growth rate for that particular treatment. And again, here you are looking at real live data. This happens to be from the Virginia DOT. What you're looking at here is the condition prior to, this is on rotting, my apologies, I should have specified the measure. We're looking at the impact of a thin overlay on rotting. On the x-axis, you have the rotting prior to the application of the treatment, and on the y-axis, the growth rate in terms of rotting. So basically here, what you're looking at is that the worse the condition prior to the treatment, the faster that segment is going to rot. Hope that makes sense. You'll notice that there was a lot of variability in that plot, and there should be, right? We're trying to, in that single plot, you have traffic, you have climate, you have structure, you have subgrade soils. If you start taking those different factors into your models, you can actually do a really, really good job of coming up with fairly decent models of performance, and that's really what you're looking at here. On the x-axis, you have rut growth predicted from the models. Y-axis rut growth actually measured. This is what we found from the data from the state DOTs and LTPP. The dashed line is the line of equality, and you'll notice that most of the points are almost, perhaps not all of them are on top of the line, but they're very close to the line, and that's good. So our predicted and our measured growth rates are almost equal to each other. I'll also point out that the red crosses are control sites. This happens to be LTPP data, so we did have control sections. Whereas the circles are sections that received the treatment, the thin AC overlay. And this is perhaps a little bit harder to see, but what we found is that for the control sections, the growth rate of rotting was higher than for the treatment sections. And if I remember the exact numbers, there were 0.038 inches for the control versus 0.031 inches for the treatment sections. In other words, the growth for the treated sections was slower than that for the control sections. A lot of information. We did this for every performance measure for every single treatment, so there are a lot of models out there. But let me go to some of the major findings from the study. Well, first, I should note that the project was completed earlier this year. It's going to be published as NCHRP Report 858, which is under publication at the moment. Now, besides all of the information that I've presented here in a lot more detail, there is a guide as an attachment to help agencies implement performance measures or performance models into their practices. The guide basically addresses, number one, the selection of performance measures. We recommended 4 measures, but an agency can decide to implement whatever measures best fit the strategic objectives of that agency. Number 2, it provides a step-by-step procedure on how an agency can gather and prepare the data to develop the performance models that will be used to characterize performance. And if you can do that, you can do service life. If you can do that, you can do life cycle cost. You can do payment management. You can do asset management. If you're able to define the impact of preservation on payment performance, which is what I've been talking about the entire presentation, then you really cracked a very important step in the decision-making process. A couple of conclusions that I would like to highlight. For many reasons, for many years, that there's not sufficient data out there, and hence, in many cases, we've relied on anecdotal evidence. The reality, at least from the data from the 8 agencies, and we in NCHRP 1438, which is now ongoing, we've gotten data from 10 states. The data are there. The data are there, and you can use those data to develop models. Now, having said that, the data do have variability, and it is possible that you may need to have to go to techniques that we as payment engineers do not necessarily often use. I'm talking about techniques like ramming regressions, robust regression, things that perhaps a new generation of engineers, I think, know pretty well, certainly not in my curriculum, but anyways, there are tools out there that we can use. And agencies, of course, should continue to strive to improve the quality of data, both in terms of accuracy and precision, but we do have lots and lots of data. This is probably overemphasizing a point that I've made already a couple of times. If we are able to quantify the effects of preservation treatments on performance, there's a lot of things that we can do with that. And here I just put, this is from 1438. Timing, what is the best timing of, for applying a preservation treatment? If you look at the literature, I believe most of the recommended procedures are based on a cost-benefit ratio, where the benefit side of the equation is performance-driven, whether you look at it in terms of service life or the area under the curve, however you define performance. So it is really, really, really important. So
you were limited to IRI, rutting, faulting, and cracking.
Cracking, transfers, and longitudinal. Well, it depended on the pavement type.
And so the challenge, a huge challenge on some of these treatments, if you're at the top of the curve, you're barely making any impact at all on any of those things. Maybe cracking, if that was your trigger. You know, so thin overlay, yeah, I could see how you get the change in IRI, but the challenge for me is to try to figure out, say for a chip seal or something like that, the distresses that we collect, I can't really prove that I've changed anything. I'm hoping to get a longer life, but I can't measure that today.
And this again goes back to the 2 effects, right? There's an initial effect. In the case of chip seal, microsurfacing, the immediate effect, I don't think you're going to see a whole lot of improvement. Rotting, and for the same matter, IRI. When you start looking at the long-term effect, and that's why data is so critical, you do start seeing that. We did find, and Gary, please correct me, but I believe we found that chip seal does slow down the deterioration rate as compared to a section that does not receive it. So it doesn't have an initial impact, but when you start looking at the long term, you do start picking it up. So
Gary Hicks from the California Pavement Preservation Center. I'm glad to see you using CAPE seals, because we found many cities and counties are using multiple treatments. They put a microsurfacing on first, and then an asphalt rubber chip seal, and then a slurry or a microsurfacing on top. And the city of Watsonville has used it for 10 years, and you can put it down on pretty poor pavements with PCIs as low as 30. So 2 layers is good, but 3 layers might even be better.
Yes, we all agree. Yeah. Well, thank you very much. Appreciate it.
The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.